Welcome everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to write functions in multiple ways and recognize function notation, how to recognize patterns in functions to determine whether or not those functions are linear, how to recognize coordinates in terms of x values and y values, how to plot points on the coordinate plane, how to recognize patterns in the graphs of linear functions, how to determine how the slope and y-intercept will affect the graph of a linear function, how to find a function value of a linear function, how to find the slope and y-intercept of a function from an equation, how to take linear equations that are not written in slope-intercept form and convert them to slope-intercept form, how to graph linear functions using slope and y-intercept, how to manipulate the slope and y-intercept to change the steepness and location of a graph to suit the needs of the question, how to find the y-intercept of a linear function given the slope and a point on the line, how to find the equation of a line given the slope and a point on the line, how to compute exponential expressions on integers and fractions, how to perform basic exponential operations and recognize like terms, how to work with positive, negative, and fractional exponents on integers and variables, how to recognize patterns in linear functions and exponential functions, how to recognize the differences between linear functions and exponential functions, how to recognize patterns in the graphs of exponential functions, how to determine how base values, coefficients, and constants will affect the graph of an exponential function, how to graph exponential functions, how to find function values for exponential growth functions, how to find function values for exponential decay functions, how to factor a number out of a polynomial in order to simplify an expression, how to recognize a binomial as a difference of squares, how to factor a binomial into a difference of squares, how to factor polynomials with a coefficient of 1 into a product of binomials, how to factor polynomials with coefficients greater than 1 into a product of binomials, how to recognize roots of a quadratic equation as being the x-intercepts of the equation, how to use factoring to determine the roots of a quadratic equation, and how to use the quadratic formula to determine the roots of a quadratic equation. How are we learning it? Through the we out here trying to function notes and the we out here trying to function assignment. When can we use this information? To recognize patterns in your spending so that you can figure out how to save enough money to buy a car, to determine the location of appliances, furniture, and walls when planning to remodel your house, to determine how long it would take to save up enough money for a down payment on a car, to calculate the amount of money in a savings account, to change the appearance of difficult tasks so that it looks more like something you were used to seeing, such as changing your grocery list into a list based on the aisles where you will find the items, to improve your ability to read between the lines and fill in the gaps that are not given, such as putting together a bookcase with directions that are incomplete, to calculate the amount of money in a savings account including interest, to calculate the amount of money owed on a loan including interest, to examine the sales trends at work to determine how much growth is occurring within the company's sales, to examine problems from your life from different perspectives in order to find the best approach to simplify the problem, and to determine the distance of a home run in the Major League Baseball home run derby. How do you know you learned it? By getting a score of 4 on the we out here trying to function assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your get it started. After that, I'll give you time to complete the we out here trying to function assignment on Desmos. At the end of class, we'll go back over the learning goals and success criteria while you fill out your before you go. Your only homework for tonight is to work on any incomplete assignments that you may have. Let's take a look now at the we out here trying to function notes. The notes begin with the learning goals and success criteria. Let's begin our notes with looking at linear functions. Now let's talk about the components of a function. A function is a relation in which each element of the domain is paired with exactly one element of the range. The domain is all of the input or x values in a function. The range is all of the output or y values in a function. Therefore, a function, meaning that for every x, there's exactly one y that matches it. So in looking at this, we're given a table here, and we're supposed to pick out the range and the domain of each of these. So first we'll do the domain, the input values. Well, our input values in this case is the month, so we're just going to list the values that apply. Well, we can see that the values are 1, 2, 3, and 4. So that is our domain, 1, 2, 3, and 4. The range, are these values here. So our range would be 2, 4, 6, and 8. So we have our domain, we have our range. Let's try another one. So here we have 0, 2, 3, and 6 for months. That is our domain. And our range comes from this column here. So we would have 6, 3, 4, and 8 as our range. So that's domain and range. Now, understanding functions. Notice here, we have a domain here, and we have a range here, and they're mapped to each other. So when x is 2, y is 8. When x is 3, y is 12. When x is 4, y is 9, etc. And the question is this a function? Remember, in order for it to be a function, there has to be one y for every x. So if I look at this, I can see that my 2 is only mapped to 8. I can see that 3 is only mapped to 12, 4 is only mapped to 9, and 5 is only mapped to 17. So therefore, this is a function because there's no split. I don't see 2 going to 2 different places. Let's look at another example. We have a domain here, and notice now the question is this a function? We have the domain here and the range here, and notice 2 is mapped to both 8 and 12. So therefore, this is not a function because 2 is mapped to 2 different places. Remember, for every x, this is our x, for every x, there can be only one y that goes with it. 4 and 5 are okay. 3 is actually okay even though it's not mapped to anything. The issue is 2. Okay, let's look at another example. So this one says for every number in the domain there can only be one number in the range. And is this one a function? Well, we have 2, 3, 4, and 5, and 2 is mapped to 8, and 3 is mapped to 8. So there's 2 numbers going to 8. The question is that okay? The answer is yes, it is okay, and this is still a function, because 2 is only with 8, and 3 is only with 8. It doesn't matter that they're both going to the same place. The issue would be if x is mapped to 2 places, but each x, 2 and 3, are only mapped to one place. They're just mapped to the same place. So yes, this is still a function. How can we tell if something's a function by a graph? Well, we use what we call the vertical line test. So again, for every x, there can be only one y. So if I pick an x like 5 here, I can see that when x is 5, y can be this number here, whatever that is, maybe 14 or so, and y can be here, which is -4. So in this case, this would not be a function because there's 2 numbers. Now the easy way to check this is what we call the vertical line test. I can draw a line anywhere on the graph, and if I draw the line anywhere on the graph and it touches the graph in 2 places, or more than one place, then it is not a function. So I can see here, I drew my line in and it touches there and there. So when x is -10, this is not a function. So therefore, it's not a function. And if it only happens once, it doesn't matter how many times. In this case, I can draw a line almost anywhere and it's going to be not a function. But if there's even one place where I can draw it and it's not a function, then the whole thing is not a function. Now what about this one? Is this one a function? Well, let's take a look. Is there any place I can draw a line? Notice I drew several lines in different places, and no matter where I drew the line, it still only crosses in one place. So even though the graph looks really funky, right? It goes up and down and up and down, I still can't cross in 2 places, so therefore this is a function. Okay, functions can be written in 2 ways. We can call it f of x equals some function, right? I can write the equation for the function there. Or I can say y equals some function. So you probably heard the term y equals mx plus b before. Well, what I'm telling you here is that it doesn't always have to be y, it could be f of x. So f of x equals mx plus b, and that means the exact same thing as y equals mx plus b. From that then, I can find a function value that corresponds to the domain value of some number, which in this case I'm going to plug in 3. So let's say I gave you that f of x, or it could be y equals, right? F of x equals 2x minus 3. And I want to know what happens when the domain value is 3. Remember, the domain is x, so I'm going to plug 3 in for x. So this becomes 2 times 3 minus 3. Now I solve, so I'm going to multiply 2 times 3, and I get 6. 6 minus 3 is 3. So when x is 3, y is also 3. And if I were to plug in any other number, so let's say this was 4, I would just plug 4 in for x. If it was -8, I would plug -8 in for x. So whatever number they give you, that's the number you plug in for x and then solve. Linear relations. What makes something linear? A linear relation occurs when the graph of the relation set forms a straight line. So we have a graph here, and we plotted all the points that they gave us, and when we did that, it forms a straight line. That's a linear relation. Notice that as the x values change by 1, the y values change by the same amount each time. Meaning that as we go through, it keeps stepping up the same amount each time. How to read a table? The columns are the vertical cells in the table. So this is a column, and this is a column. And then we have rows, which are the ones that go horizontally or side to side. These are our rows. We always label the columns. So in this case, we're calling this one time in months, and this one temperature in degrees. And then we put in our table. So we fill it in with the data points. Now the columns separate the two variables. So this separates time from months. And the rows separate the actual data. So this is a data point. This is a data point. This is a data point, and this is a data point. So in this case, we're going to try to recognize what pattern we see in the columns. So if we look here at the time, we see that each time we go down one level on the rows, that we're adding 1. So we could say that time is moving up from one row to the next, and the pattern is consistent, right? We didn't have add 1, add 2, and then add 1. We're consistently adding 1. Next, let's look at the temperature. Well, is there any kind of pattern here? Well, from here to here, we're adding 5, and then adding 5, adding 5, and adding 5. So therefore, the temperature is moving up by 5 from one row to the next, and the pattern is also consistent. So the temperature is going up by 5 degrees every 1 hour. That's what we can say based on the pattern we see from the table. Now from that, can we tell if these patterns are linear or not? Well, if the changes in the data are consistently changing by the same amount, and that amount is in the form of addition, it is a linear relation. So let's take a look at the table. So we have our months, and we look and see that there is a steady change. We're adding by 1 month each time. And in rainfall, we can see that we have a consistent change also. We are adding by 2 inches each month. Therefore, if we were to plot these points, it would look like this, and therefore we can see it does form a straight line, and yes, it is linear because we have a consistent change of addition and a consistent change of addition. Let's look at another example. So we have our months here, and we can see that they are adding by 2 each time. So therefore, yes, there is a consistent change. In this case, we're adding by 7, and then 7 again, and 7 again. So yes, there is a steady change, and it changes by 7 home runs. So therefore, is this linear? Well, we have a consistent change of addition, and we have a consistent change of addition here. So therefore, this is linear. Now we can take a look at it another way in terms of perimeter. So this is kind of a geometric application to this. So if we have the perimeter of this block here, we know that this side is 2 and this side is 4. So now we're going to see that this side is also 4 and this side is 2. We know that perimeter means the sum of all the sides, or adding up all the sides. So this is 4 plus 4, which is 8, plus 2 is 10, plus 2 is 12. So that's my perimeter for the first one. Now we do it for this one. This is 2, and this is 4. So that means this side also has to be 4, and each of these sides has to be 2. So that's 2, 2, and 2. So if we add all these up, this is 4 plus 4 is 8, plus 4 is 12, plus 4 again is 16. And then again, we add these up. This is 4 and 4, and then 2, 2, 2, and 2, 2, 2, and we get 20. So now, if we were to do this by the number of rectangles and the perimeter, so this is one rectangle here, which was a perimeter of 12, 2 rectangles was a perimeter of 16, and 3 rectangles is a perimeter of 20. Therefore, we want to know, is this linear? Well, we're adding by 1 each time here, so that's consistent and addition. We're adding by 4 each time here, that's consistent and addition. So yes, it is a function, and it is linear. Now let's take a look at axes. So within the coordinate plane, we should notice that there's these lines that break up the x and y's. The axes are the thick lines that break up the positive and negative values. So if we look here, we have our x's here that go this direction, and we have our positives on this side and our negatives on this side. And they're broken up by this line here that represents the negative y's and the positive y's. So they break up each other and create positives and negatives in each of these boxes. The x-axis is the one that goes side to side, and it's usually labeled, but sometimes it's not. This is the x-axis that goes side to side. The y-axis is the vertical axis, the one that goes up and down. This is the y-axis that goes here. From that, we form what we call quadrants. Quadrants are these boxes that are created from the axes. So this is a box, this is a box, this is a box, and this is a box. And we label them I through IV, or 1 through 4. So this is quadrant 1 right here. This is where we begin. And then we go counterclockwise this way around to create the other boxes. So this is quadrant 2, this is quadrant 3, and this is quadrant 4. Notice each quadrant represents positive or negative x values and positive or negative y values. So for instance, quadrant 1 represents positive x values and positive y values. Quadrant 2 represents negative x values and positive y values. Quadrant 3 represents negative x values and negative y values. And quadrant 4 represents positive x values and negative y values. Now, how do we plot points on the graph? Well, first of all, we're given ordered pairs. Ordered pairs are single components of a relation containing an x value and a y value. So what that means is we're given an x and a y. For instance, this is an ordered pair. -2, 3. So the way this works is my x goes first and then my y. If you have trouble remembering that, just remember that they go in alphabetical order. So x, then y. So my x is -2. So I'm going to go along the x-axis and find -2, which is here. And my y is 3. So I'm going to go along my y and go up to 3, right there. And I'm going to plot my point. That represents -2, 3. Then we have -4, -6. Well, -4 on my x-axis, so I'm going to go find -4 on the x's, right there. And then -6. So I'm going to go down and find -6, which is here, and plot that point. Then I have 5, 3. So x is 5, so I'm going to go and find where x is 5, which is here. And y is 3, so I'm going to go find 3, which is right there. And there's that point. And lastly, I have 1, -3, so x is 1, so I'm going to go find 1 on the x-axis, which is here, and -3 on the y-axis, which is here. And I plot that point, and now I have plotted all 4 of these ordered pairs. Now part of this is being able to plot the points, but the other part of it is being able to recognize the points once they're already graphed. So in this case, I'm given some points and asked to find where those ordered pairs are. So let's look at A, which is here. Well, I can see that my x value is 1, 2, 3, and my y value is down 1, 2, 3, 4. So it's x equals 3, y equals -4. So that would be my point for point A. Then I can do point B. Point B is right here. So I went to the right 1, 2, so x is 2. Y is 1, 2, 3, 4, 5, 6. So I would be at 2, 6. Then I find C. C is here. So that's -1, 2, 3, 4. And my Y is -1, 2. So C is -4, -2. Then I do D. D is right here. So that's -1, 2, 3, 4, 5. And -1. So -5, -1. Then E. E is here. So that's 1, 2, 3, 4. And then -1, 2. So it would be 4, -2. Then F is here. So that's -1 and -1. And then G is here. So G is 1, 2, 3, and then 1, 2, 3, 4, 5. So 3, 5. And then H is here, which is -1, 2, 3, 4. So -4 and 1, 2, 3. So -4, 3. And so that's how I can look at graphs of coordinates and be able to figure out what their ordered pairs are. There's a video here now that shows you how to check your coordinates in Desmos. You can watch that as well. Now let's talk about slope. What is slope? Slope is a rate of change involving x values and y values. Slope is known as for being the change in the dependent variable over the change in the independent variable. Now what does that really mean? That really means that slope is the change in the y values over the change in the x values. So it's always y over x. And the next part you need to know is the y-intercept. The y-intercept is the point where the linear function crosses the y-axis. So we have a line here, and we can see that the y-axis goes here. So where do they intersect? Well, they intersect right there. That is what we call the y-intercept. So in this case, our y-intercept would be 2. Slope-intercept form. Slope-intercept form is written as y equals mx plus b. And what does that mean? M is the slope, and b is the y-intercept. Y and x are my variables that stay variables so that I can plug numbers in and see what they come out to be. So m is the slope and b is the y-intercept. Now how can I remember that? The easiest way I remember this is m represents the slope because it's a slippery slope to get hung up on your x. So think about it in terms of relationships. People that are involved in relationships and they break up, there's usually that one person in that relationship that's always hanging on to the relationship that's already dead. That's the slope. That's M. It's a slippery slope to get hung up on your ex. They are not together anymore. But the M is always trying to hang on. Notice how close they are. So M is trying to hang on, and it's a slippery slope to get hung up on your ex. Now B, on the other hand, is alone. Not attached to anybody. B is lonely. And lonely people ask the questions, why am I alone? Why does no one want me? Why does no one think I'm cute? That's B. B is always asking the y questions. Those are the y-intercept questions. So that's the way I remember it. It's a slippery slope to get hung up on your x, and why am I alone? So that's the way I remember slope and y-intercept. Now, let's go ahead and pick out the slope and y-intercept from an equation. So we're given an equation, y equals 2x plus 4. And we want to know what is the slope of that line. Well, we know that the slope is the one that's attached to its x, right? So it's a slippery slope to get hung up on your x. So the one that's attached to the x in this case is 2. So the slope is 2. The y-intercept is the lonely one. Why am I alone? Well, the lonely one is 4. So my y-intercept is 4. So that's how I pick out the slope and y-intercept given an equation. Let's look at another example. We have y equals negative 3 halves x minus 3. Well, same thing. It's a slippery slope to get hung up on your x. So the slope is the one that's attached to the x, which is negative 3 halves. So that's my slope. And my y-intercept is the lonely one. Well, the lonely one in this case is negative 3. So B is negative 3. So that's how I find the slope and y-intercept from an equation. Now, how do I write the equation from a graph? Well, I'm going to use the slope, which is the change in the y values, over the change in the x values. So I'm going to pick out 2 points. Luckily, they've already done it on the graph for me. And I picked this point, and I'm going to calculate the change in y. So how far down in this case did I go to get to here? Well, I went down 1, 2. So my change in y is negative 2. And I went to the right 1, 2, 3. So that's positive 3. So my change in x is 3. So it's negative 2 over 3, which is negative 2/3. So that's my slope. Well, the y-intercept is the y value when x equals 0, which in this case is right here. So my y-intercept is 3. So now I know my slope and I know my y-intercept. So I'm going to plug that into y equals mx plus b. Remember, the slope goes where m is. So the slope is negative 2/3. So this should say y equals negative 2/3 x. And b is 3. So I'm going to plug that in. So my equation for this line would be y equals negative 2/3 x plus 3. Now, how do I graph a linear function? Well, first thing I need to do is pick out my slope and my y-intercept. Well, in this case, my slope is negative 1/2 because that's attached to the x. Now, my y-intercept, notice there's nothing here. There's no lonely people. So how do I say none in math terms? Well, that's 0. So my y-intercept is 0. So now when I graph this, the first step is I plot the y-intercept. Well, my y-intercept is 0. So I'm going to go along my y-axis and find 0, which is right here. And I plot my point. The next step is I'm going to use the slope to plot my second point. Remember, this is change in y over change in x, or you might have heard it in the past as rise over run. We're going to talk about it as change in y over change in x. So my change in y is negative 1. So I go down 1. And my change in x is 2, so I'm going to go to the right 1, 2, and plot my point. So now I have my first 2 points. The next step is just to connect the dots and draw a line between them. So I'm going to connect the dots. And now I have a linear function that is graphed that goes through 0 and has a slope of negative 1/2. Now, what do I do if the equation's not in slope-intercept form? Well, that presents a problem. I can't actually graph it unless it's in slope-intercept form. So I know that it needs to look like y equals mx plus b. So I need to get y by itself. So anything that's not y, I'm going to move to the other side. So I'm going to begin with this 4x here. And I'm going to move the whole thing, because if I just move the 4, then the x is still here. Well, I don't want the x to be there. I want the x to be on the other side. So everything must go. So if this is positive, I'm going to subtract it. If it was negative, I would add it and get rid of it and move it all to the other side. So I'm going to subtract 4x. Well, 4x minus 4x is 0, so that's gone. So now I'm left with 10 and negative 4x over here. So I'm going to rewrite this as negative 2y is equal to negative 4x plus 10. Now I'm going to get rid of whatever's over here with the y. Well, I got a negative 2 over here, and it's being multiplied by y. So I'm going to undo that by dividing. So I'm going to divide both sides by negative 2. That gets rid of this, because negative 2 divided by negative 2 is 1. So it's just 1y. So that's what I want, just y. And then this gets divided to both of these. So negative 4x divided by negative 2 is positive 2x. And 10 divided by negative 2 is negative 5. So I end up with y equals 2x minus 5. Here's my slope. Here's my y-intercept. Now I can graph that equation. Let's look at another example. We have 4y plus x is equal to 64. Well, same thing. I'm going to go ahead and get rid of the x first. So it's a positive x, so I'm going to subtract x to get it to the other side. And I'm left with 4y on this side. And I got negative x and 64 over here. So I got 4y is equal to negative x plus 64. Now I need to get rid of this 4. The 4 is being multiplied by y. So I'm going to undo it by dividing both sides by 4. And 4 divided by 4 is just 1. So that's 1y, which is what I want. And now I have negative x, which is really negative 1x, divided by 4, and 64 divided by 4. Well, negative 1 divided by 4, I can't actually do that, so I'm just going to leave it as a fraction. So that stays as negative 1/4 x. And 64 divided by 4 is 16. So I'm left with y equals negative 1/4 x plus 16. One more example. We have 4y minus 4 is equal to 3x. Well, the x is already over here, so the only thing I got to get rid of is this 4 and this 4. So I'm going to get rid of this one first. So I do that by adding 4 to both sides, which leaves me with 4y is equal to 3x plus 4. Now I'm just going to get rid of this 4. This 4 is being multiplied by y, so I'm going to undo that by dividing. So I divide both sides by 4. And I get 3 divided by 4, which is just 3/4 x, and 4 divided by 4, which is 1. So I'm left with y equals 3/4 x plus 1. Now what if I'm given 2 points and asked to find the slope? Well, first thing we need to remember is that coordinates are written in the form x and y, right? So the x goes first and the y goes second. And that slope is the change in the y over the change in the x. So what we're going to do is we're going to take these points and we're going to subtract the y values and put that as my numerator, and subtract the x values and put that as my denominator. So when I do that, I get 1 minus 2. Those are my y's, so that's my change in y. So my change in y is 1 minus 2. And my change in x is 2 minus 4. So that's change in y over change in x. Now when I do that, 1 minus 2 is negative 1. And 2 minus 4 is negative 2. And when I do that, a negative divided by a negative just becomes a positive. So this is just 1/2. So my slope for that line that goes through those 2 points is 1/2. Let's look at another example. So what is the slope of the line that passes through -3, -3, and 2, -6? Again, coordinates are written as x and y. So this is my x, this is my y. This is my x, this is my y. And slope is change in y over change in x. So I'm going to calculate that by subtracting my y values first. So -3 minus -6. And then I'm going to subtract my x values, which is -3 minus 2. So I get -3 minus -6 and -3 minus 2. And when I simplify, this really becomes plus positive. So -3 plus 6 is 3. And -3 minus 2 is -5. So it's 3 over -5, which is just -3/5. There's a video here also that shows you how to graph linear functions in Desmos. So you can go ahead and watch that. Now what is point-slope form? We use point-slope form if we know the slope and 1 point on the line. We can still create the equation for the line even though we don't have the y-intercept. And here's how we do it. We know that slope is y equals mx plus b, and we plug in the slope for m. So whatever the slope that's given to us, we plug that in for m. We plug in the x value of the coordinate. So we're given some ordered pair, and we're going to plug in the x part here, and we plug in the y coordinate here, and now we're left with only one variable, which is b, and we could solve then for b and get the y-intercept. So let's take a look at an example of this. So it says, what is the equation of the line through 3, -2 with a slope of 2/3? So first thing is we take our y equals mx plus b, and we're going to plug in what we know. We'll plug in the slope first. So the slope is 2/3. That goes in for m. So now this says y equals 2/3 x plus b. Then we'll plug in the x value of the point we know. Well, the x value is 3, so we plug that in for x. And then we plug in the y value for y, which in this case is -2, so we plug that in for y. And we get -2 is equal to 2/3 times 3 plus b. Now we can solve for b. Well, we get 2/3 times 3, so which when we multiply this out, we get 6/3, which is the same thing as 2. So we got -2 is equal to 2 plus b. Now we just solve by subtracting 2 from both sides. And we're left with b is equal to -2 minus 2 is -4. So b is -4. So that is the y-intercept. Now we can put that into the equation. So we have y equals 2/3, because that was our slope, x, and b is -4, so that's our equation. Now let's look at another example. We have -4, -1 as our point, and the slope is -2. So we're going to start with y equals mx plus b, and then we're going to plug in what we know. Well, we know the slope is -2, so that goes in for m. So this becomes y equals -2x plus b. Then we're going to plug in our x value. Well, our x value is -4, so we're going to plug that in for x. So this becomes y equals -2 times -4 plus b. Then we plug in our y value. Our y value is -1, and that goes in for y. So this is -1 equals -2 times -4 plus b. Now we just solve for b. Well, -2 times -4 is +8. So that's -1 is equal to 8 plus b. We're going to get rid of this 8 by subtracting. So we subtract 8 from both sides. And we get -1 minus 8 is -9. That's equal to b. Now we plug this back into our y equals mx plus b form. Y equals -2x. And then our b is -9, so it's -9. Let's look at one more example. We're given a point 4, 2, and the slope of -3/2. So we're going to use the form y equals mx plus b, and we're going to plug in the slope for m, which is -3/2. So that goes there. And we're going to plug 4 in for x there. So we got y equals -3/2 times 4 plus b. Then we're going to plug 2 in for y, which is here. So it becomes 2 equals -3/2 times 4 plus b. Now we're going to go ahead and solve for b. So when we do this, we get -12/2, which is the same thing as -6. So 2 equals -6 plus b. We're going to add 6 to both sides to get rid of that 6, and we get 2 plus 6 is 8. So b is 8. Now we're going to plug that back in. So we get y equals, and we know that the slope is -3/2 times x, plus our y-intercept, which in this case is 8. So that goes there, and that's how we write the equation using point-slope form. Now let's take a look at quadratic functions. Now, what is an exponent? An exponent is a number that tells you how many times to multiply the base number by itself. So for instance, we have 2 to the third power. 2 is what we call our base number, and it tells us that we're going to multiply 2 times itself 3 times. So that's really 2 times 2 times 2, which is 8. Now let's talk about positive exponents. So positive exponents mean that the number above here, the number of times we're going to multiply it times itself, is a positive number. So we have 5 squared. Well, that means that we're multiplying 5 times 5, which in this case is 25. Then we have 5 to the third power, which is 5 times 5 times 5, which is 125. And then 5 to the fourth power is 5 times 5 times 5 times 5, which is 625. So we can do this with any exponent. We can take any base number and raise it to an exponent and multiply it by itself a certain number of times and solve. Now what about 0 and 1 exponents? So 5 to the first power. Well, 5 to the first power is just 1 5, right, times itself, so 5, that's it. So that's just 5. Now 5 to the 0 power. So there's 0 5s, and that's equal to 1. Now please make sure that you understand this. Any number raised to the 0 power will always be 1. So not 0, but 1. So 5 to the 0 power is 1. 2,000 to the 0 power is 1. 200 million to the 0 power is 1. So any number raised to the 0 power is just 1. Now combining like terms, if we look at this, we're going to combine like terms, and the rule is, in order to combine like terms, they have to have the same exponents and same variables. And if they do, we're going to add the coefficients. So for instance, we have 2x and x. Well, they're both x's, so they have the same variables, and they have the same power, same exponent. Really, it's imaginary exponent of 1. So we can just add these. 2x plus x is 3x. We have 3x squared plus 4x squared. Again, same variable, they're both x's. And the powers match, so we just add the coefficients. That's 3 plus 4, which is 7x squared. We can do it with subtraction as well. So we have 6x cubed minus x cubed. Well, again, same variable, same power. So now we can go ahead and subtract. So 6 minus 1 is 5x cubed. Now we have 7x to the fourth minus x cubed. Well, again, same variable, but this time they do not have the same power, so we cannot combine them. It just stays 7x to the fourth minus x cubed. Now when we multiply or divide exponents, so the rule is this: when we multiply or divide exponential terms, even if they do not have the same exponents but have the same variable, we can still do it. The rule is we multiply or divide the coefficients and add or subtract the exponents. So if we're multiplying, we're going to add the exponents. So this is 2 times 1, so that's my coefficient. And I have an x to the first and an x to the first, so I'm going to add those exponents. So I get 1 plus 1 for my exponents. So 2 times 1 is 2, and 1 plus 1 is 2, so it should be 2x squared. So look at another example of multiplication. So we have 3x cubed times 4x squared. Now with this one, again, we're going to multiply the coefficients, so 3 times 4, and we're going to add the exponents, so 3 plus 2. We end up with 3 times 4, which is 12x, and 3 plus 2 is 5, so we get 12x to the fifth power. Now division is just the opposite, so we're going to divide the coefficients and subtract the exponents. So we get 6x to the seventh divided by 2x to the third, so we're going to divide the coefficients, so 6 divided by 2, and then subtract the exponents, so it's x to the 7 minus third power. So 6 divided by 2 is 3, and 7 minus 3 is 4, so we get 3x to the fourth. Now here we have 7x to the fourth divided by x cubed. So again, we're going to divide 7 divided by 1, and x to the fourth minus 3, which is 7 divided by 1 is 7, and x to the 4 minus 3 is first power. And whenever it's the first power, we don't need to put it there, so it's just 7x. Now what if we have the coefficient and variable inside of parentheses and the power outside? Well, when we do that, we're going to raise the power by multiplying the exponents. So in this case, we have 2x, and this is x to the first, and we're going to multiply the powers for each of these. So this is really 2 to the first power times 2, and x to the first power times 2. So that's really 2 squared times x squared. Well, 2 squared is 4, and x squared is just x squared, so it's 4x squared. Now let's look at this one. Again, same thing. This is 3 to the first and x to squared. So we're going to multiply each of those by the power out here, which is 3. So we got 3 to the first times 3 and x to the second times 3. Well, we know that 3 to the first times 3 is 3 cubed, and 2 times 3 is 6. So we got 3 cubed times x to the sixth, and 3 cubed is 27. So it's 27x to the sixth. Now for this one, we have x squared times y cubed, and we want the whole thing squared. So again, we're going to multiply it. So x squared times 2 and y to the third times 2. And we get x to the fourth, y to the sixth, because we multiply 2 times 2 is 4 and 3 times 2 is 6. Now we have x y squared z cubed to the sixth. So we're just going to multiply each of the exponents by 6. So we get x to the first times 6, and y to the second times 6, and z to the third times 6. And we're just going to multiply these out. So 1 times 6 is 6, 2 times 6 is 12, and 3 times 6 is 18. So we should get x to the sixth, y to the 12th, z to the 18th. Now let's take a look at negative exponents. So a negative exponent looks like this, where it's 5 to the negative second power. Now here's the rule with negative exponents. When we're working with a negative exponent, we're going to rewrite as the reciprocal, meaning instead of this being 5 to the negative second, we're going to write it as 1 over 5. And then we're going to change the power to a positive. So 5 to the negative second becomes 1 over 5 squared. So I made the power positive and put it under 1. Now I just do it like normal. So 5 squared is 25, so this is 1 over 25. Now 3 to the negative third power. So again, that becomes 1 over 3 to the positive third power. 3 to the positive third power is 27, so it's 1 over 27. Now we have x to the negative sixth power. So we're going to flip that and it becomes 1 over x to the positive sixth power. Now let's take a look at fractional exponents. For instance, we have 25 to the 1/2 power. So what we're going to do is we're going to take the base number, 25, and we're going to raise it to the power of the numerator. So it would be 25 to the first power. And then the denominator is going to make up the root we're going to take. So in this case, it'll be the second root or square root. So the way that looks is we're going to have 25 to the first power, which is just 25. And then we're going to take the square root of that, just like this. So we need to know what number multiplied by itself gets 25. Well, we know that 5 times 5 is 25, so the square root of 25 is 5. Let's look at another example. We have 3 to the 1/3 power. So again, we're going to take 3 to the first, and we're going to find the cube root of it. Well, what times itself 3 times equals 3? Well, we should recognize that it doesn't come out evenly. There's no whole number that does that. So we're just going to leave it as cube root of 3. Now we have x to the 2/3 power. So what we're going to do is we're going to take x and raise it to this power. So it should be x squared. And then we're going to take the cube root of that. So the third root of x squared. And we should notice that there's no number that we can multiply by itself 3 times to get x squared. So we just leave it as cube root of x squared. Now what if we have a negative and a fractional exponent? Well, we do the same thing we did on the previous two. We're going to go ahead and flip it and make it positive. So we're going to, x to the negative 1/2 becomes 1 over x to the 1/2 power. Just like that. Now we know that we're going to take the 1/2 power, and that becomes x to the first, and then we're going to take the square root of that. So that becomes 1 over the square root of x to the first, which is just x. Now, first of all, what is a linear function? A linear function occurs when the graph of a relation set forms a straight line. So when we plot the points, if it forms a straight line like this, that means it is a linear function. Now, what does a linear function look like as a table? Well, if we look at the table here, the rule is if all of these in each column, so this column and this column, if the change is all consistent and it's addition, then we say that the set is linear. So for instance, we have 1, 2, 3, 4. So we can see that it is consistent, there is a consistent pattern, and the pattern is that we're adding by 1. So that's addition. So now if we look at this side, we have 2, 4, 6, 8. Again, consistent pattern, addition by 2. So is there a steady change in the number of months? Yes, we're changing by 1 month each time. Is there a steady change in the amount of rainfall? Yes, there is. We're changing by 2 each time. So therefore, we could say, yes, this set is linear. And if we were to graph it, it would look something like this and form a straight line. So that's a linear function based on a table. Now from graphs, again, the rule is they form a straight line. So this is an example of a linear function. This is also an example of a linear function. As is this one. It can go up or down. It can be really steep or really flat. This is another example. Again, really flat and going downward. This one's steep and going downward. So all of these form what we call linear functions. Now, how can we recognize linear functions as an equation? Well, it should be able to form y equals mx plus b. Or it could be f of x equals mx plus b. An example of this would be y equals 1/2 x minus 3. This would be an example of a linear function. Notice the powers for both y and x are 1. Now what is an exponential function? An exponential function is a function that forms a curved line that has a line that it will never cross. For instance, this is an exponential function. It's a curved line, it's a single curve, it starts low and works its way up. It could go this direction also, start high and work down. But it has a line it never crosses. Notice this line gets really flat here at the x-axis. It will never cross the x-axis. So there's a line here that forms that it'll never cross. In this direction, it'll keep going and going and going and get really steep. How can we recognize exponential functions from a table? Well, first of all, the rule is the number of months, my x values, should be changing by a consistent amount, and it should be addition. And my y values should be changing by multiplication. So in this case, we have the months. So this is 1, 2, 3, 4. Well, is there a steady change in the number of months? Yes, there is, and it's changing by 1 month each time. Now here we have 2, 4, 8, 16. There is a steady change, and it is multiplication. We're multiplying by 2 each time. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So we're seeing a steady change, and it's multiplication. It is doubling, or multiplying by 2 each month. So therefore, is this exponential? Yes, it is. And if we were to plot these points, it would look something like this and form this curve. Now, what do exponential functions look like as graphs? They always form a curve, a single curve. So for instance, this is an exponential function. This, even if I shift it over, it's still considered an exponential function. If I have it go downward, that's an exponential function. And if I have it go below the x-axis, still an exponential function. All of these are examples of exponential functions. Now, exponential functions are of the form y equals a to the x times b. Or it could be f of x equals a to the x times b. Here, an example of this is y equals 3 to the x times 4. Now, if you notice in all of these, y has a power of 1, and x is the power of the base number. So these are exponential functions. So how can we compare these? So the question says, based on the table below, does each table represent a linear function, exponential function, or neither? Well, if we look at this one, we have 1, 2, 3, 4, 5. So this one's consistent and going up by 1. So it could be either linear or exponential at this point. Then we have 3, 6, 12, 24, 48. Well, 3 plus 3 is 6. 6 plus 3 is not 12, so it's not linear. So 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So that means it's got to be exponential. Now this one, 2, 4, 6, 8, 10. So we do have a consistent pattern. We are adding by 2. So it could be either linear or exponential. Then we have 1, 2, 3, 4, 5. Well, 1 plus 1 is 2, plus 1 is 3, plus 1 is 4, plus 1 is 5. So they're both consistent, they're both addition, therefore it's got to be linear. Now this one says -2, -1, 0, 1, 2. So again, we're adding by 1 each time, so it could be either linear or exponential at this point. Then we go 8, 4, 0, 4, 8. So here we subtracted 4, then we added 4, So it's not a consistent pattern, so therefore it's neither linear nor exponential. Now we have our graphs. We're supposed to determine whether it's linear, exponential, or neither. Well, this first one does have a curve, but it curves in both directions, which we know that exponentials only curve in one direction, so therefore this is neither linear nor exponential. Then this one we have a straight line. Well, we know a straight line forms a linear function, so that one is linear. This one has a single curve, so that one is exponential. Now looking at the equations, we have y equals 2/3 x minus 4. Well, both of them have a power of 1, and we have both the x and y, so that one we said was linear. It also looks like y equals mx plus b, so we know it's linear. Now this one is y equals 2/3 times -4 to the x power. Well, we should notice that looks like b times a to the x, which is exponential. So this one is an exponential function. This one says y equals 2/3 times the absolute value of x minus 4. Again, it looks similar to this one. We have x to the first power and y to the first power, but the absolute value changes things, so it is neither linear nor exponential. Now, let's take a look at exponential functions with bases less than 1. So when the base of an exponential function is less than 1, the curve will remain above the x-axis, and the curve will be the same, but the curve will go down instead of up. For example, we have y equals 1/3 to the x power times 4. So notice this is smaller than 1, and a normal curve goes up, but if we have a value here, a base number less than 1, it's going to go downward as we go from left to right. So it looks exactly the same as 3 to the x, except it's just mirrored over to the other side and going this direction. Now what if the base is negative? Well, when the base is negative, the graph will flip below the x-axis and will go down instead of up. For instance, we have y equals -3 to the x times 4. So here, it's going to flip and go downward below the x-axis. It's going to be exactly the same graph as 3 to the x, but it's just going to be down this direction. So it's going to be like it was reflected down below the x-axis. Now what if we were to add a constant? So when a constant is added to an exponential function, the graph will shift up or down, but the curve will stay the same. So if we had y equals 3 to the x times 4 plus 2, then it would look like this. So it would look exactly the same as y equals 3 to the x times 4, except we're going to slide it up 2 units. So now the line it doesn't cross is y equals 2 instead of the x-axis. Now, what if it was 3 to the x times 4 minus 2? Same thing, except now it's going to shift down and go this direction. So it's the same as 3 to the x times 4, except we're going to slide it down, and now the line it won't cross is y equals -2. Now, what if we do a sum of exponents, meaning we add something to the exponent? Well, that will cause the graph to shift to the right or to the left. So for instance, we have y equals 3 to the x plus 2 times 4. So what that should look like is, notice it's the same curve, And because this is in the exponent, we're always going to go opposite. So you would think that we'd go x plus 2 means we're going to slide to the right. But because it's in the exponent, we're going to go opposite. So it becomes x minus x plus 2 becomes a shift to the left. So notice it's the same graph as 3 to the x times 4, except we slid it to the left 2 units. Now what if it was 3 to the x minus 2 times 4? Well, same thing. We're going to slide it, but this time we're going to slide it to the right 2, because we always go opposite when we talk about exponents. So we slide it to the right 2, and it becomes this graph. It should look exactly the same as 3 to the x times 4, except we're going to slide it to the right. There's a video here that shows you how to check exponential functions in Desmos, so you can go ahead and watch that video as well. Now, what is exponential growth? Exponential growth is a function where a quantity increases by the same rate in each time period. For an example, money in a savings account. So I put money into my savings account, my money increases with interest, and it goes up exponentially. Now, what is exponential growth formula? The exponential growth formula is f of x, or y, is equal to a times 1 plus r to the x power. So A is our starting amount. That's how much we start with. If we were talking about money in a bank account, that's how much money we put into the account. R is the rate of change, meaning how much interest are we gaining. X is the amount of time. So let's say it goes monthly and we're doing it over 12 months. 12 months would be my X. Now notice the value inside the parentheses will always be greater than 1 with exponential growth because I'm adding 1 plus some number. It doesn't matter what number that is, it won't be negative, so we know it'll always be greater than 1. So let's look at exponential decay now. Now exponential decay is a function where a quantity decreases by the same rate in each time period. An example of this would be radioactive decay of a fossil. So when something dies, it eventually becomes just bones, right? We know this through archaeology. It becomes just bones. And what happens is there's a certain amount of carbon in that bone. After a while, the carbon starts to decay. It starts to wither away. It starts to evaporate. From there, we can tell how old the fossil is based on the amount of carbon that's still left. So that's radioactive decay of a fossil. Now, exponential decay, the formula looks like this. F of x equals a times 1 minus r to the x. So it's the same as growth, except this is minus r instead of plus r. A is still the starting amount. That's how much we start with. So if we were talking money that we owed, well, that might be A, right? So that's our starting amount, how much we owe. R is the rate of change. How much are we paying each month? X is the amount of time. So let's say we're paying it off in 12 months. And then notice the value inside the parentheses will always be less than 1 because it's 1 minus some value. And we know that R is never going to be negative. So it's 1 minus some value, so that means it's going to be something less than 1. Now, how can we recognize growth versus decay in graphs? Well, growth is always going to go up. Decay will always go down. So exponential growth goes up, exponential decay goes down. How do we recognize it from equations? Well, exponential growth equations always have a base value greater than 1. So it could look like this. Y equals 3 times 1 plus 0.4 to the x. So obviously that's greater than 1 when we add those together. Or it could be something like this where they already added it together for you, where it's y equals 3 times 1.04 to the x, which obviously this number is greater than 1. So that's growth. Decay always is less than 1 inside the parentheses. So we have something like this, y equals 1 minus 0.4 to the x. Or they might have already done it for us and had y equals 3 times 0.06 to the x, which both of these we can tell are going to, when we simplify them, are going to be less than 1. So that's decay. So how can we tell? Let's look at an example. We have f of x equals 1/2 to the x. Well, 1/2 is less than 1, so that is decay. We have 3/2 x. Well, that's bigger than 1, right? Because that's 1 1/2, so that's growth. 7/8. Well, that's smaller than 1, so that's decay. 4/3, again, that's bigger than 1, so that's growth. And 1/3 is less than 1, so that is decay. Notice it didn't matter that they put a coefficient, it didn't matter that they messed with the exponents. This is the only number that matters. If it's bigger than 1, it's growth. If it's smaller than 1, it's decay. Let's look at a word problem for exponential growth. It says the population of Chicago in 2016 was estimated to be 35,000 people with the annual rate of increase of 24%. What is the population in 2019? So first of all, we're going to go ahead and use our formula of f of x equals a times 1 plus r to the x. And we're going to plug in the starting amount. Well, what did it start out at? Well, it started out at 35,000, so that goes in for a. So this is f of x equals 35,000 times 1 plus r to the x. Then we're going to plug in our rate of change. Well, we can see that it changes by 24%. Well, 24% we need to write as a decimal. So this is really 24.0%, right? So we're going to move the decimal back 2 places. 1, 2. So it should change to be 0.24. And then lastly, we're going to plug in the amount of time. And the amount of time between 2016 and 2019 is 3 years. So this is f of x equals 35,000 times 1 plus 0.24 to the third power. We'll solve that using a calculator. And when we do that, we end up with 66,731.84 people. So that should be the population of Chicago in 2019. Let's look at another example. So it says we opened up a bank account 4 years ago with $300. You have a 7% interest rate on your account. How much money do you have now? So again, we're going to start with our exponential growth formula. So we're going to plug in the starting amount. Our starting amount was $300. So we plug that in for A. Then we're going to plug in our rate of change for R. It says we're going up by 7%. So we move the decimal back 2 places. So that's 0.07 is our rate of change. And then we're going to go by the amount of time. We're going to plug that in. The amount of time was 4 years. So we plug 4 in for X. And then we solve using a calculator. And when we do that, we end up with $393.24. Now let's look at exponential decay. So this time the population in Chicago was decreasing by 24%. So we start here with our equation of a times 1 minus r to the x. We know it's minus because we're decreasing. And we're going to plug in the starting amount. The starting amount was 35,000, and that goes in for A. Then we plug in our rate of change. Our rate of change is 24%, so we're going to move the decimal back 2 places. 1, 2. So that's 0.24. And then we plug in our amount of time. The amount of time is from 2016 to 2019. That's 3 years. And then I solve using a calculator, and I get 15,364.16 people. Let's look at one more exponential decay word problem. So it says you opened up a bank loan 4 years ago with $300. You pay 7% of the remaining balance each year. How much money do you owe now? So again, it's decay because the amount of money we owe is going down. So if we start with f of x equals a times 1 minus r to the x. So the first thing we do is plug in our starting amount. Our starting amount is $300, so that goes in for A. And we're making payments, so we're going to plug in our rate of change. We're paying 7% each time, so it's 7. We're going to move the decimal back 2 places, so 1, 2, so that's 0.07. Lastly, we're going to plug in the amount of time. The amount of time is 4 years, so that's 4. We plug that into our calculator, and we get that now we owe $224.42. There's a video here that shows you how to check exponential functions in Desmos, so you can go ahead and watch that video as well. Now let's take a look at exponential functions. Understanding multiple forms of multiplication. So when we are multiplying two numbers together, particularly when one of them is a variable, we write them as joined together. So we write them like this. So we're multiplying 4 times x. So we write them joined together. We can also use parentheses to do this. So we can write 4 and then parentheses x. They mean exactly the same thing. They're just giving indication of multiplication. So distributive property. So it says what would happen if we wanted to multiply 4 times 2 less than some unknown number? So instead of just being 4 times x, we want it to be 4 times some grouping of a number. So in this case, x minus 2. So we write it just like this, 4 times x minus 2. The distributive property states that we will multiply 4, so the number outside, by everything that's inside the parentheses. So this becomes 4 times x and 4 times negative 2. And then we can just go ahead and combine whatever terms we can combine at the end. So in this case, we get 4x minus 8. Because 4 times x is 4x, and 4 times negative 2 is negative 8. So then how do we solve something like this? X plus 4 times x minus 2. Well, maybe you heard of this term before, FOIL, which means first, outside, inside, last. So you multiply the firsts and then the outsides, so this one and this one, then the insides, then the last ones. Well, that might be what you've heard in the past, or maybe you haven't. But does it work for all polynomials? So can I do it with this? Now FOIL doesn't really help. So the easiest rule is multiply every term in the first one by every term in the second one. Pretty simple. So we take x and multiply it by x. We take x and multiply it by negative 2. Then that's all it for the x's. Now we do the 4. So 4 times x and then 4 times negative 2. And now we go ahead and combine these. So x times x is x squared. Negative 2 times x is negative 2x. 4 times x is 4x. And 4 times negative 2 is negative 8. Now we just combine the like terms. X squared, we have to leave that by itself. But we do have a negative 2x and a positive 4x. So we can combine those. So negative 2x plus 4x is positive 2x. So we get x squared plus 2x minus 8. So what about trinomials? So what if it's 3 terms? It's no different. We do the same thing. So we take x squared and multiply it by x squared. We take x squared and multiply it by 4x. We take x squared and multiply it by negative 6. Then we do it for the second term. Negative 3x times x squared. Negative 3x times 4x. Negative 3x times negative 6. And then we do it with the 2. 2 times x squared. 2 times 4x. 2 times negative 6. And this looks like a lot of stuff, but once we combine like terms, it shouldn't be so bad. So we get x squared times x squared is x to the 4th. We get x squared times 4x is 4x cubed. X squared times negative 6 is negative 6x squared, and so on. And we end up with this. Now we just combine like terms. So we're going to find all the x to the 4ths. Well, this is the only x to the 4th. Then we find all the x cubes. Here's an x cubed, here's an x cubed. So we have 4x cubed minus 3x cubed. When we combine those, we just get a single x cubed. Then we do all the x squareds. Then we do all the x's. Then we do all the constants. And when we combine them, we end up with x to the 4th plus x cubed minus 16x squared plus 26x minus 12. Now factoring. Factoring is a term that means simplifying a problem by determining the factors of the expression. So we need to be able to pick out a common factor that exists within a number or a set of numbers. So in this case, let's just look at 36. What are the factors of 36? Well, we have 1, 2, 3, 4, 6, 9, 12, 18, and 36. These are factors because I can multiply all of these numbers by something and get 36. Or another way to look at it is 36 is divisible evenly by all of these numbers. So these are factors. So factoring is really just a reversal of the distributive property. For instance, with the distributive property, we had something that looked like this earlier. So we had 2 times x minus 4. Well, we multiply 2 times x and 2 times negative 4, and we get 2x minus 8. Now, if we were to factor this, we're looking for something that's in common between the two of them. Well, we know that 2x is divisible by 2 and negative 8 is divisible by 2. So I can pull that out, and I end up with 2 times x minus 4. So really it's the same thing. So I just divided each of them by 2 and put that outside. So factoring in this way is exactly the opposite of the distributive property. So let's look at some examples. So we have x squared minus 4x. So we're looking for something that's in common, that we can divide out of both of them. Well, we have an x in both of them, so we could divide that out. So when we do that, we have x times something is equal to x squared minus 4x. Well, we know that we need to pull out an x, so we're going to divide x squared by x. So x squared divided by x is just x. And then negative 4x divided by x is just negative 4. So we get x times x minus 4. Let's look at another example. We have x squared y minus 4xy squared. So we need to figure out what's in common. Well, we have a single x in common here, right? Because this x squared, there's not a squared here, so we can only pull one x out. And we have a y and a y squared, so we can pull one of those out as well. So we're going to pull out an x and a y. So we know that's what it's going to look like. xy times something is equal to this whole thing. Well, when we divide by an x, we're left with one x here. When we divide by a y, it takes the y away, so it's just 1. So all we're left with here is just an x. And then we have this minus 4, that stays. When we divide by x, the x goes away. And when we divide by y, we get just a single y. So we should end up with xy times x minus 4y. Let's look at another example. We have x squared minus 4. So we're looking for something that's in common. Well, all we have is an x here, and all we have is a constant here. So there's nothing in common there. So there's nothing we can factor out. So it's not factorable. So we just leave it as it is. So this is its most factored form for now. So what is a difference of squares? A difference of squares is subtraction of two terms that are perfect squares. For instance, x squared minus 1. So remember, difference means subtraction, so it's got to be subtraction. And each of these numbers needs to be a perfect square. Well, we know that x squared is the quantity x to the second power, and 1 is just 1 squared. So this is a difference of squares. So this would be an example. So how do we factor a difference of squares? We're going to use the following methods. So anytime we start with something like this, and we have a number squared minus a number squared, it becomes a plus b times a minus b. Okay, so it's just something you have to memorize. So a squared minus b squared is equal to a plus b times a minus b. So let's look at an example. X squared minus 4. Well, if we rewrite this, if we put it in this form, this is really x squared minus 2 squared. So when we write that, we would write x plus 2 times x minus 2. And that would be our factored version. So look at another example. We have x squared minus 4. We said that that is... So let's check our work by distributing. So we said that x squared minus 4 is equal to x plus 2 times x minus 2. Well, let's go ahead and distribute this and see if it works. So we're going to multiply x times x and x times negative 2, and then 2 times x, and then 2 times negative 2. So we get x squared here minus 2x plus 2x minus 4. We combine our like terms. Negative 2x plus 2x is just 0, so this becomes x squared minus 4. So we did it correctly. Let's look at another example. We have 25x squared minus 16. Well, 25x squared is really 5x squared, and 16 is really 4 squared. So we can rewrite this as 5x plus 4 times 5x minus 4. And that's our factored version. So look at another example. 25x to the 4th minus 16. Well, we have a power of 4 here, but is that still a perfect square? Well, we know 25 is a perfect square, And then x to the fourth is really x squared squared. So we can go ahead and enter that in. So this is 5x squared plus 4 times 5x squared minus 4. And that would be our difference of squares. Another example, 3x squared minus 12. Well, we can see that 3 is not a perfect square and 12 is not a perfect square. However, we can see if we can use our method from yesterday as well. So we can see if we can factor out a common factor first. So is there anything in common between 3 and negative 12? Well, we can see that 3 is a factor of both 3 and negative 12. So let's go ahead and factor that out. So 3x squared divided by 3 is just x squared, and negative 12 divided by 3 is negative 4. Well, now we have this 3 here. Now we have a difference of squares inside the parentheses, so we can factor that. So this is really x squared and 2 squared. So this would be x plus 2 times x minus 2. So this becomes 3 times x plus 2 times x minus 2. Now, what is a quadratic? A quadratic is an expression or equation that is of this form: ax squared plus bx plus c. So notice the squared term is here, that we have an x squared, and we have some other x and then some constant. A, b, and c are all numbers, so those are not actually variables. So an example would be 3x squared plus 2x plus 4. That would be an example of a quadratic. So if I asked you to factor this quadratic, x squared plus 5x plus 4, the solution is going to be of this form: x plus m times x plus n, and m and n will be some number. So we need to figure out what numbers need to go in these two spots. And the way we do it is by using the x method. So we're looking at the same question, and here's what we do. We place c in the top. So c is 4, so this goes up here. Then we place b in the bottom. b is the middle number, so this goes here. Now we're going to write out the factors of c. So what are the factors of 4? Well, we have 1, 2, and 4. So those are my factors. Now I need to figure out which two of those numbers are going to multiply to equal 4 and add to equal 5. Well, I have 1 times 4 is 4, and when I add those two together, I also get 5. So I'm going to go ahead and put each of those in each of these sides. It doesn't matter which one goes where, as long as I have 1 and 4 on each side. Then I'm going to place those two values into the solution. So I start with x plus m times x plus n. I'm going to plug 1 in for one of them and 4 in for the other one. So I get x plus 4 times x plus 1. And that would be my solution. Let's look at another example. We have x squared minus 6x plus 8. So same thing, place c at the top. So c is 8, so that goes here. Place b in the bottom, which is negative 6. So that goes there. Then I'm going to write out the factors. What are the factors of 8? Well, I have 1, 2, 4, and 8. Now, which of those are going to multiply to equal 8 and add to get negative 6? Well, remember, these can be both positive or negative. So I'm looking at negative 1 times negative 8 is positive 8, but it's also equal to negative 9. So that's not the answer. What about this one? So negative 2 and negative 4. If I multiply those two together, I get positive 8. And when I add them together, I get negative 6. So that would be my solution. So it's negative 2 and negative 4. So I place those in my x and then add them to my solution, which started as x plus m times x plus n. Well, I'm going to plug in negative 2 for one of these and negative 4 for the other one. So I get x minus 4 times x minus 2. One more example. We have x squared minus 4x minus 12. Well, I place c at the top, which is negative 12. I place b at the bottom, which is negative 4. Then I write out the factors of c. So what numbers multiply to get 12? Well, I got 1, 2, 3, 4, 6, and 12. Now I need to find two numbers that multiply to equal negative 12 and add to get negative 4. So I know in order to get a negative when I multiply, one of them has to be positive, one of them has to be negative. So one of these has got to get me close to 4. So if I do this, I have 2 and 6 are 4 away from each other. So I just need to make sure that when I add them, the bigger number is negative so that it stays negative. So I'm going to make this negative 6 and positive 2. When I multiply those together, I get negative 12. When I add them together, I get negative 4. So I go ahead and add those to my x. Then I place them into the solution. So I start with x plus m times x plus n. And then I'm going to plug negative 6 in for one of them and 2 in for the other one. And I get x minus 6 times x plus 2. Now what if the a value is not 1 like in the previous examples? So in this one we have 5x squared minus 18x plus 9. Well, we're still going to use the x method, but we have to add a little bit to it later on. And this becomes the x box method. So the way we start is we're going to multiply a times c and put that in the top. So 5 times 9 is 45. And then we put b in the bottom just like before, so that's negative 18. And then we're going to write out the factors of a times c. So what are the factors of 45? Well, we can see that the factors are 1, 3, 5, 9, 15, and 45. So now which one of those is going to add up to be negative 18? Well, this is positive, so we know that they have to match. The signs have to match. So we need 2 of them that are going to add up to be 18, which we can see would be 3 and 15. So that would be negative 3 and negative 15, because that'll give us negative 18 total. So we have negative 15, and this should be negative 3. Now we're going to do the box part. So that's the x part. Now we're going to do the box part. So we're going to make a table with 4 squares, just like this. And we're going to place ax squared in the top left box. So that's 5x squared. So that goes here in the top left. Then in the bottom right, we're going to put c, which is 9. So that goes there. Now we're going to place negative 15x and 3x into each one of the boxes. And it doesn't matter which one you place it in. So we'll put negative 15 there and 3x here. Now we're going to factor out what we can, trying to find a common factor. So between 5x squared and 15x, there's a 5x in common. So that's what we would factor out. So we'll go ahead and just put it at the top of the box. Then we'll do this one, 3x and 9. Well, 3 is in common between those two, so we'll put a 3 at the top. Then we go acrossways. So we have 5x squared and 3x. Well, the only thing in common there is an x. And then 15x and 9. Well, we have a 3 in common there. So now we have 5x and 3 and x and 3. And now we just place it into our solution. And now we're just going to check the signs to make sure they're correct. We know that the signs need to match so that it's 9, which they do here. And we need to make sure that we add up to be negative 18. So this is 5 times negative 3 is negative 15. Minus 3 is negative 18. So we did it correctly. Let's look at another example. We have 2x squared minus 11x plus 15. So again, put a times c in the top. So a times c is 2 times 15 is 30. And put b in the bottom, which is negative 11. So we need 2 numbers that multiply to get 30 and add to get negative 11. So we write out the factors of 30, and we get 1, 2, 3, 5, 6, 10, 15, and 30. Well, we know that 30 is positive, so then we need to have 2 numbers that are both the same sign, which add to get negative 11. Well, 5 and 6 gives us 11, so if they're both negative, that would give us negative 11. So this would be negative 5 and negative 6. So we go ahead and place that there. Now we move to the box part. So there's our box, and we put in ax squared here in the top left, so this is 2x squared. And we place c in here in the bottom right, so that's 15, so that goes there. Then we place these parts here, so negative 5x and negative 6x go in each of these boxes. And again, it doesn't matter which one goes where. So there we go. Now we just need to figure out what the common factors are. So we'll start here, 2x squared and negative 5x. Well, the only thing we have in common there is x. And then we have negative 6 and 15. Well, they have a 3 in common. Then here we have 2x squared minus 6x. Well, we have a 2x in common. And then 5x and 15 has a 5 in common. So we have x minus 3 and 2x minus 5. And we place those into our solution. So now we have 2x minus 5 and x minus 3 as our answer. Now there's a video here using Symbol Lab to show you how you can check your work with factoring. So go ahead and watch that video. Okay, what are roots? Roots of functions are the points on the graph of a function where the y values are 0. Another way to think of this is where the graph touches the x-axis. So we call these roots, we also call them sometimes roots, zeros, solutions, and x-intercepts. So all of those are different things that roots can be called in different ways. So what does a root look like? It's an x-intercept, or where the line crosses the x-axis. So it crosses here, and then it comes back down and crosses here. We call those the roots. So how do we find the roots of a quadratic? Well, the first step is factor the quadratic. So factor it any way you can, and then solve for the roots. So when we get here, we have x squared minus 5x plus 4. We would use our magic x, and once we do that, we should see that x minus 4 times x minus 1 is equal to 0. So we factor this out. Now we take each of those parts and set them equal to 0. So x minus 4 is equal to 0, and x minus 1 is equal to 0. Now we just solve for x. So we add 4 to both sides, and we get x equals 4. We add 1 to both sides, and we get x equals 1. So the zeros, or the roots, or the x-intercepts, whatever you want to call them, those ones for this equation are x equals 4 and x equals 1. Let's look at another example. We have x squared minus 5x is equal to 0. So again, we factor this, and we can pull an x out of this. So we get x times x minus 5 is equal to 0. Now we set each of those parts equal to 0, and that includes the x. So x can equal 0, and x minus 5 can equal 0. Well, x minus 0 just stays as is. It's just x equals 0. So that's one of the roots. The second one now, we add 5 to both sides, and we get x is equal to 5. So x equals 0 and x equals 5 are the roots for this quadratic. Now what about quadratics that can't be factored? So not everything comes out evenly. So not all quadratics can be factored. For instance, this one, x squared minus 5x plus 3 equals 0. This is a non-factorable quadratic. So when we get these non-factorable quadratics, we have to use what's called the quadratic formula. So what is the quadratic formula? Quadratics will always appear as ax squared plus bx plus c equals 0. And from that, we can create the quadratic formula, which says this: x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's take a look at an example of how that works. First thing we need to know before we get started, though, is what is the discriminant? The discriminant is the part under the square root. If the value under the square root is positive, then we have two roots. And if the value under the square root symbol is negative, there are no roots. So that's why we call it the discriminant, because it discriminates here against negative roots. So if it ends up negative, then we know we don't have to do any other work. It's no solution. Okay, so let's take a look here. So we're given x squared minus 5x plus 3 is equal to 0. And we're asked to use the quadratic formula. So we're going to plug in. So negative b, so that becomes negative 5, which is positive 5. Plus or minus negative 5 squared minus 4 times a, which is 1, times c, which is 3, over 2 times a, which is 1. And we end up with this. So all I did was take and plug in to the formula. Now we can go ahead and start to work the problem. So negative 5 is just positive 5. Negative 5 squared is positive 25. And then negative 4 times 1 is negative 4 times 3 is negative 12. And then 2 times 1 is 2. So we end up with this. Now we just simplify under the radical. So 25 minus 12 is 13. So we get 5 plus or minus square root of 13 over 2. Now, notice there is no perfect square root of 13, so we just leave it as is. And we make this a plus, so this is 5 plus square root of 13 over 2. And then the minus part comes in, so this is 5 minus square root of 13 over 2. So anytime you see this plus or minus, that means we're going to do two things. We're going to add it and then subtract it. So we're going to do both to it. So here's our addition, here's our subtraction. These are our two roots. So look at another example. We have 2x squared minus 5x plus 3 is equal to 0. So we're going to plug it into the formula. So we plug negative 5 in for b. We plug, again, negative 5 in for b here. We plug 2 in for a, and we plug 3 in for c, and then we plug 2 in for a down at the bottom. We get this. We simplify. Negative 5 is just positive 5. Square root of 5 squared is 25. And then negative 4 times 2 is negative 8 times 3 is negative 24. And then 2 times 2 is 4. So we end up with 5 plus or minus 25 minus 24 over 4. Well, 25 minus 24 is 1. And then the square root of 1 is just 1. So now we end up with 5 plus or minus 1 over 4. So now we're going to go ahead and solve this. So this is 5 plus 1, which is 6, over 4. 6 over 4 is equal to 3 halves. And then we do it again. 5 minus 1 is 4 over 4, which is equal to 1. So our roots for this one would be 3 halves and 1. Let's look at one more example. We have 3x squared minus 5x plus 3 is equal to 0. So we plug everything in, and we end up with negative 5 plus or minus the square root of negative 5 squared minus 4 times 3 over 2 times 3. And when we simplify that, negative 5 is positive 5. Negative 5 squared is just 25. And then negative 4 times 3 is negative 12. Times 3 is negative 36. And then 2 times 3 is 6. So we end up with 5 plus or minus 25 minus 36 over 6. Well, what we should notice is when we combine these, we end up with negative 11. Well, going back to our idea of a discriminant, we know that if there is a negative under the radical, there are no roots. So in this case, we would just say there are no roots, or we'd say no solutions. So how do we know that there are no roots? If we take this equation and put it into Desmos, it looks like this. Well, we can see that it still forms a parabola, just like all the others do, right? That U shape. But notice it's above the x-axis and it never comes down and touches. So there are no roots there. Okay, just a reminder, you need to simplify under the radical all the time. So let's say you end up with square root of 12 under the square root symbol. You always need to simplify it as much as possible. And the way you do that is you're going to try to find the greatest square factor. So for instance, what we think about the factors of 12, and we recognize that the factors are 1, 2, 3, 4, 6, and 12. And we want to pick out which ones are perfect squares. Well, we know that 1 and 4 are perfect squares, but we only want the biggest one, so 4 is the biggest perfect square. So that's really 4 times 3. So we could take the square root of 4. The square root of 4 is 2. So this becomes 2, and then we leave whatever's left under the square root, which is 3. So this becomes 2 square root of 3. Simplifying fractions, remember once you're done and you get your answer, make sure that you simplify the fractions as much as possible. So let's say I get 4 plus or minus 2 times the square root of 3 over 2. If this value in the denominator goes into both evenly, then you need to go ahead and divide it. If it only goes into one, then you leave it, because it has to go into both. So 4 divided by 2 is 2, and 2 square root of 3 divided by 2 is just square root of 3. So we end up with 2 plus or minus the square root of 3. There's a video here now that you can watch that shows you how to check your roots for quadratic equations using Desmos. So go ahead and watch that video. Let's talk now about how to sign in to Desmos to complete your work. So what we're going to do is you're going to click on the link to go to the assignment, and it should take you to a page that looks kind of like this. And right here where it says sign in with Google, we're going to click there. And it's going to pop up with our email accounts. You're going to click on your school email account, and it should already have you logged in because you should have already been logged in using Google Classroom. From there, I'm just going to click start the activity, and it will take me into the assignment and allow me to begin. So that's how you will log into Desmos using Google. Let's take a look now at the We Out Here Trying to Function assignment. The assignment begins with the learning goals and success criteria. If we scroll down, we can see the link that'll take us to the Desmos activity. When we click on that link, it should take us to a page that looks like this. We'll go ahead and click Start the Activity. The activity begins with the learning goals and success criteria. We'll go ahead and click Next. There's an introduction video here for you to watch. So go ahead and watch that video. Now let's take a look at linear functions. So we're given the opportunity to fill in a table, write an equation, and draw a graph of what linear functions look like. So for this one, we're looking at linear functions, and if we remember back to Math 1, linear functions say that for every change in the x, we have to have a consistent pattern in the x's, and then we also have to have a consistent pattern in the y's, and the y's have to have a consistent pattern of addition. So here, in order for this to be linear, we go from 4 to 7. That means we're adding 3. So we have to continue adding 3 each time. So 7 plus 3 is 10. 10 plus 3 is 13. 13 plus 3 is 16. So there's my table. Now for the parent function, I'm going to write what the parent function for a linear function is, which is y equals mx plus b. And then I'm going to graph one. So I'm just going to use the line tool here, and I'm going to click somewhere on here and extend it out. And there is my linear function. So we'll do that for linear. And then we'll do it for exponential. Remember, exponentials have to have consistent change as well, but it needs to be multiplication. So we would multiply 4 times 2 to get 8. So we'd multiply each of these by 2. We'll state what the parent function is for exponential functions. And then we'll graph one. Remember, the graph of an exponential function should look something like this. And then we'll move on to the next one. The next one is quadratics. You'll just fill in these two tables. Remember, they should be symmetrical. So if this is 0 and this is 1, this is 2 and 2, 4. This should be 4 and 1. Then you'll state what the parent function is, which should be y equals ax squared plus bx plus c. And then we're just going to state what it looks like. It should look like a U-shape or a parabola. After that, we're going to look at all the tables that we've created, so they should all be here. And we're going to state how they're different from each other and how they are the same. We'll do the same thing with the sketches of the graphs. So here's all our graphs, and we're going to state how they're different and similar. And lastly, we'll look at the equations and state how they are different and similar. At the end, there's a video for you to watch. Go ahead and watch that video. Once you're done with the assignment, we'll go back to our Google form and click Next. This will take you to your Before You Go. Go ahead and fill out your Before You Go and then submit your work on Google Classroom.